paper I'm presenting is Das Mill, distilling across scales for a multi-instance learning classification of histological WSIs. The use of multi-instance learning, or MIL, for classifying whole slide images has increased in recent years because feeding the gigapixel WSIs into the modern neural networks is mostly unfeasible and time-consuming. To address these limitations, MIL has emerged, which treats the WSI as a bag composed of many patches and using attention mechanisms to aggregate them into a single representation for classification. However, existing MIL approaches are noted to be intrinsically flat and neglect the pyramidal information provided by the WSI. To address this gap, this paper proposes a pyramidal graph neural network combined with knowledge distillation. It is termed Das Mill, or distilling across scales. This approach aims to profit from the multi-resolution structure of the WSIs by utilizing distinct GNNs to provide contextualized features, which are then fed to attention-based MIL modules for computing back-level predictions. Furthermore, through knowledge distillation, agreement across predictions are encouraged, which help preserving a diversity in information across different resolutions. The paper emphasizes that by transferring knowledge across scales, the classifier self-improves as information flows during training. The effectiveness is demonstrated on two well-known datasets, Chameleon 16 and TCGA lung cancer. Specifically, the Chameleon 16 dataset contains 400 WSIs from two different medical centers at 40x magnification. And the TCGA lung cancer dataset contains 1,000 WSIs, also at 40x magnification. Here is a diagram of the overall proposed framework. The authors claim that while existing works take into account interscales interactions by mostly leveraging trivial operations such as concatenation, their approach aims to promote the information flow through the different resolutions. The two key elements here are, first, on the left, a GNN module based on message passing, which takes advantage of the natural structure of the multi-resolution WSI. And secondly, on the right, a knowledge distillation module that uses the most effective resolution to guide the training for the other resolution. The entire framework begins with a feature extraction, where the authors employ a self-supervised learning approach called Dino to extract relevant patch-level representations at multiple resolutions. This is done to encourage feature diversity across scales. Next, to capture the global context of the WSI, the authors use a pyramidal graph neural network module that allows patches to exchange local information. The input in two scales undergoes two graph layers. First, they are treated as two independent subgraphs A1 and A2, and then the two subgraphs are processed jointly by considering the entire graph as A. Next is the knowledge distillation module. The authors observe that the higher resolution predictions generally outperform the lower resolution ones. To make use of this, two additional optimization objectives are introduced. First is a knowledge distillation term, LKD, that aligns the back-level predictions between the two resolutions. Second, an instance-level alignment term, LCRIT, that encourages the instance-level criticality scores between the two resolutions to be consistent. Critical scores are essentially importance scores, which quantify how important each original patch is to the overall prediction. Finally, the overall optimization objective is a combination of the standard cross-entropy loss from the back-level predictions and the above-mentioned two knowledge distillation terms. Here we can look at these key elements in the proposed framework in detail. First, the pyramidal graph neural network. Looking at it as a whole, its input contains features in both resolutions, and there are two subgraphs as well as the one that connects them together. The second line further specifies that features in each resolution first enter each subgraph at that resolution, and then they're jointly considered by the graph A, which joins the two subgraphs according to the neighboring connections. This way, features in different layers are not simply concatenated, but are associated in a manner that is logical given the multi-resolution structure. Next, the two knowledge distillation terms are essentially to ensure consistency between resolutions. First, the KL divergence is a statistical distance that measures how different one probability distribution is from another. Since the back-level predictions, although at two resolutions, will have a one-to-one relationship, then the KL divergence can be used here. For the criticality term, however, it is obvious that Z1 is the lower resolution layer, so each node will correspond to multiple nodes in Z2. Therefore, what the graph pooling here does is that it groups a number of Z2 values together and then maintain consistency with Z1. And at last, we can see that the overall objective function contains the loss for each individual subgraph, the back-level consistency, and the instance-level importance values. Here are some experimental details. The WSIs are pre-processed so that background patches are removed. Then, non-overlapped patches from the foreground regions are used. The authors used the Adam optimizer and a cosine annealing scheduler. The final overall prediction comes from the classifier on the higher resolution scale. For the Chameleon 16 dataset, training and validation are in the ratio of 9:1. And for the TCG-A dataset, the aim is to classify the two cancer subtypes present in the dataset. The performance assessment using accuracy and AUC metrics is in accordance with previous literature. Here is a table demonstrating results from multiple algorithms, including the proposed approach. Two things can be observed. One, the joint exploitation of multiple resolutions is generally more efficient, as the multi-scale results appear higher than most single-scale results. And two, the proposed approach achieves best results in both datasets, especially on Chameleon 16, with 3.3% accuracy and 1.9% AUC above the state-of-the-art. The authors did note that although most other methods use different feature extractors, the subsequent results will prove the benefit of the proposed framework. Here, the table on the left demonstrates that the pipeline achieves better result with a moderate balancing coefficient for the knowledge distillation module. This means that the lack of knowledge distillation would negatively affect the performance. The figure on the right tests the GNN in the proposed approach against another recent graph mechanism across different feature extractors. Both of these results show that each module of the proposed framework has contributions to the final performance. This table compares performance between single-scale and multi-scale. Within single-scale, better results are obtained with higher resolution, and with multiple scale, the combination of 10x and 20x magnifications performs better, while the authors also note that different datasets and tasks may benefit from different scale combinations. The strength of the paper lies in its novelty. The use of neighborhood connectivity in GNN is both original and intuitive. The selections of back-level and instance-level knowledge distillation terms are also insightful. Another strong point of the paper is the clear explanations of concepts and procedures. The ablation studies also sufficiently demonstrate the benefits of different modules in the framework. Finally, the datasets used and the code are both public. The weakness of this paper could be the omission of a section discussing its limitations. A remark on the relevance of this paper selection to this homework. In the optimization objective function, two terms are involved respectively, the KL divergence and cross-entropy. Both can be used to measure distance between distributions, and in this work, the KL divergence is used to measure two predictions, and the cross-entropy is used to measure between prediction and data.